So today, I want to give you a very brief introduction to a field of computer science that I do some work in. It's a field called computational geometry. And it basically studies algorithms for geometric problems. And a real typical computational geometry result will start with something like a statement like let S be a set of n points, sometimes more specifically in the plane. So here is a set, for example, of 3 points. And algorithms then, at least for algorithms for these point sets, will try and compute some quantity or some structure associated with that point set or whatever other set of geometric objects you might have. And applications of computational geometry show up everywhere. So we'll just look at a couple of the most classic problems and solutions because they give some nice examples of clever algorithms. They illustrate the field a little bit, but also they make critical use of efficient data structures that we have studied in this course. But before that, just the sort of super brief intro is one of the things that computers tend to be not so good at, that we're really good at, is analyzing geometric shapes just by looking at them. So when I say, here's a set of points, I can draw them on the board, and right away your brain starts to process these and gets all kinds of, somehow intuitively computes all kinds of information about those points, like their shape, for some sense. What's the shape of a set of points? Or their extent, how wide they are, how tall they are. All of that just sort of appears. But not so easy for computers, right? So we have this visual system that lets us see everything at once, whereas computers, well, we know how they work. They have this processor that executes, instructions on basically two pieces of data at a time. So it's not so easy for them to do this kind of stuff. And so what they need, if you want to study geometric problems with computers, is you need some primitives that work on just a small number of points. Then you can then use those primitives on those small number of points to get a bigger picture of the structure of a larger point set. And one of the most useful such primitives is what's called the orientation test, or sometimes the right turn test, or the counterclockwise test, or the clockwise test. And that's a test that takes 3 points, let's say A, B, and C. Now remember, in a computer, points will be stored as pairs of coordinates. Let's say they could be integers or floating points. The x coordinate and the y coordinate, the x coordinate and the y coordinate, the x coordinate and the y coordinate. And the sort of fundamental question is, well, what's the shape of those 3 points? Or more precisely, if I walk from A to B, and then turn at B towards C, which direction am I turning in? Am I turning clockwise or counterclockwise? So there's sort of 2 ways that could happen. You go from A to B, and here you turn clockwise to get to C. Or they could be in a different kind of structure like this. A, B, C, where when I go from A to B to C, I actually make a counterclockwise turn. So turn that way in this case, and in this case I turn that way. So that telling the difference between those 2 things is called an orientation test. And of course, there's a third possibility, which is that when I go from A to B to C, I don't turn at all, or I turn 180 degrees. So that would be the case, which we usually call degenerate. That's where A, B, and C are all contained in a single line, in which case, there is no orientation if they're collinear. So with this test, you can do an amazing number of things, answer lots and lots of questions. And so the question is, how do you do this test? So does anybody know how you do this test? Anybody taking linear algebra? No. So it turns out that if you make a little matrix out of the coordinates, that's a 3 by 3 matrix. It's the coordinates listed on each row with a 1 at the end. And you take the determinant of that. Does anybody know what that gives you? Recognize that one? Yeah? But do you know what it means? What it tells you? Yeah. Yeah?
It's for calculating the area of a triangle.
It's for calculating the area of a triangle. So it actually calculates the area of the triangle A, B, and C. And do you remember something funny about this calculation? Sometimes it gives you something that doesn't look like an area. Sometimes it gives you a negative value. So sometimes it gives you a positive value. Sometimes the area of the triangle is 0, so it gives you 0. The area of the triangle is 0 and AB is 0 all on the same line. And sometimes it gives you a negative value. So when does it give you a negative value and when does it give you a positive value?
Like a value triangle is going to be the negative value.
Here?
Yeah.
Maybe. So if those 3 points are oriented clockwise, you get one kind of value. I don't remember if it's negative or positive. And if they're oriented counterclockwise, you get the other kind of value, negative or positive. So in both cases, the absolute value gives you the area of the triangle. But in one case, if you're making a right turn here, it'll be, let's say, negative. And if you're making a left turn here, it'll be positive. So the sign of that result tells you whether you're making a left turn or a right turn. So you just compute this determinant, and you don't actually care about the value. All you care about is whether the sign is positive, negative, or the value is 0. That tells you whether it's a right turn, a left turn, or collinear. So that's sort of our basic operation. And one of the things you can do with that is if I have 2 line segments, let's say A, B, C, and D. Well, line segments can do have different relationships to each other. For example, you can have 2 line segments like this that don't cross. You can have line segments like this that they would cross if one of them was a bit longer. And then you can have line segments that actually do cross. And so, one of the things that we'll end up doing, and one of the things we'll look at today, is finding all the intersections between, pairwise intersections between a set of line segments. So you need a test to tell whether 2 line segments cross each other. And you can make such a test out of this orientation test. It turns out that 2 line segments cross if, when you do these orientations, you keep getting the same result. So you get clockwise when you go from C to D to B. When you go from B to A to D, you get clockwise. When you go from D to C to A, you get clockwise. And when you go D to A to C, B to A, and this one here, ABC, the original one. If they're all the same, so they're all clockwise, then you get a crossing, or if they're all counterclockwise, then you get a crossing. We could just switch the labels here, and they would be counterclockwise. So you can detect crossings between line segments using this right turn test. You can detect all kinds Okay, so that's the primitive. We want to express anything we can do. That's something small enough that a processor can, we know how to program it and make a processor do it. There's no high-level understanding of the point set, just a few points, and we can figure out their relationship to each other. And we want to use that to build more complicated things. And the classic problem in computational geometry is the convex Hall problem. There are lots of ways to state the convex Hall problem. Some more formal than others. Some which require things like notion of measure or area. Some which just require the notion of convex combinations. I'm not going to try and be formal or fancy. I'm just going to give you an intuitive definition. So, convex Hall of a point set like this is intuitively, imagine that these points are nails and I've hammered it to the chalkboard here. Each one is sticking out of the chalkboard. And I take a big elastic band and pull it, stretch it so that it encircles all of these nails. Now it's actually a pretty tight one, so when I let it go, it's going to snap tight. And then it snaps tight on the convex Hall of this point set is this convex polygon that you get here. So it'll always be a convex polygon. The vertices of the polygon will be some points in your set. And convex just means that if I take any 2 points inside the polygon, inside this pink region, then the whole line segment joining those 2 points is also inside the pink region. So, some people will tell you the convex Hall is the smallest convex shape that includes all the points, or they might say it's the set of all convex, it's the set of points that can be expressed as convex combinations of the points. Don't worry about that. Keep this elastic band staying in mind. So if I start somewhere on the convex Hall and I start walking, so I walk to this vertex, and then to this vertex, and then this vertex, and then this vertex. I reach these vertices and I make turns. What kind of turns do I make? So I'm going around this thing clockwise, and when I hit the vertices, what kind of turn do I make? Yeah, it's always a right turn, so we always turn right a little bit here, we turn right a little bit here. If I'm facing down, I'm turning right here, and so on. So somehow this notion of convexity has to do with these right turns that we know how to test. Okay. If I ever find myself walking along the convex Hall, or what I think is a convex Hall, and if I started out going clockwise, and I find myself making a left turn, well then there's a problem there, because the inside is supposed to be here on the right-hand side, but if I make a left turn at this vertex, well that actually means that this thing is not convex, because here are 2 points very close to this vertex, and if I look at the line segment in between them, it's actually not contained inside it. So these convex Halls, basically, if I walk around them in the clockwise direction, I'll always make right turns, and if I turn around and walk in the other direction, I'll always make left turns. So the orientation test will always tell me the same thing. So this was actually one of the first problems studied in computational geometry, and already in the year of my birth, 1973, a famous mathematician named Ron Graham gave a linear time algorithm for this that has since become known as Graham's, or not linear time, n-log n time algorithm for this. It's become known as Graham's scan. Now, Ron Graham is an interesting character in himself. Around this time and a little bit later, so he's quite an athlete, gymnast, and especially a juggler. So at some point he was able to juggle consistently 7 balls at a time. That's really, really hard. So 3 balls, anybody can learn to do that in a day. 4 balls is already quite difficult, and it gets really hard. So he was, one of, I wouldn't, maybe not one of the best in the world. There were probably professional clowns who could do better, but very, very good. You can find pictures of him online in his office. So one of the things, if you've ever learned to juggle, has anybody ever done that before? Yeah. And so usually you get a book that teaches you the motions. You practice for a day, and you get, by the end of the day, you're pretty good at juggling 3 balls. What happens the next day? Well, you maybe forget, but what else happens? Usually the next day you have a sore back because you've done so much bending over and picking things up. So you can find a picture of him online. In his office, he had installed a giant skirt that attaches around his waist and is pinned to the top corners of the office so that when he juggles and drops a ball, it rolls back down to him in this skirt. Because when you're trying to learn how to do 7 balls, you spend a lot of time dropping and picking up balls. It's nice if they're this break down. Okay, so enough about Ron Graham. So first thing you do when you don't know how to solve a problem is, so again, point set, this convex hull somehow describes the shape of the point set in some rough way. In fact, it's a useful thing to have if you want to do things like testing if 2 objects intersect. So you can have some very complex objects like this one and this one, and you want to know if they intersect. Well, that's actually a fairly complicated thing to test. A good first approximation is to first check if their convex hulls intersect each other. And if their convex hulls don't intersect each other, then the objects themselves certainly don't intersect each other. And it turns out you can test very quickly. There's a sort of binary search routine that can test very quickly if 2 convex polygons intersect each other. So if the polygons have n vertices each, you can test in log n time if they intersect. So that's sort of a good first attempt. And if you think of large-scale simulations where there's lots of pairs of objects you're worried about them intersecting, you can quickly eliminate lots of pairs just by doing this.
Yeah, you say it's n time. N is the number of points outside of the.
No, n is the number of points in the plane, so the total size of the point set. So n points in here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n is 11 in this case. Yep.
When we're talking about these points, do each of them are they defined as vectors or
They're,
points in space?
each one is, in this case, is represented as a pair of integer or floating point coordinates. So they're points in the Cartesian plane. Okay, so when you don't know how to understand a problem, first try and break it down into 2 problems. And for convex hulls, one of the things you can do is reduce it to 2 separate problems, one of computing the upper hull, what's called the upper hull, and one of computing what's called the lower hull. So these things are also easy to define in some physical way. For an upper hull, imagine that I take a piece of string with some, I don't know, dumbbells on the end, and I pull it so that the 2 ends go past the leftmost point and the rightmost point, and then I drop it, then I'll get something like this, right? So the string will get hung up here on the point that has the smallest x coordinate, as well as on the point that has the largest x coordinate. compute both the upper hull and the lower hull, well then I can read off the convex hull from that because both the upper hull and the lower hull start at the point with the smallest x coordinate and finish at the point with the largest x coordinate. And don't worry if there's points with equal x coordinates for now. That's easy to do. Okay. So, and I think it's pretty clear that if I show you how to compute the upper hull, well, you can do the same thing for the lower hull. You could negate the y coordinates and turn the picture upside down or something. Okay. All right. So how to compute the upper hull of the point set? So it turns out that a really powerful technique in computational geometry is to first sort the points. So in this case, try and make this interesting if we can. So here's a set of points. You start by sorting the points by their x coordinates. And now we can call the points P1, P2, P3, 4, 5, 6, P7 in order of increasing x coordinates. We know how to sort. We've seen 3 algorithms. So step 1 is sort. We can do that at OML again. And actually, the rest of the algorithm is now going to run in linear terms. That's why I sometimes say linear time when I think of this algorithm, because it's really just the sorting that makes the longest. And here's what we're going to do. We're going to keep a stack. So, data structure we've seen before. And that stack is going to, if you look at the stack starting at the bottom and going up to the top, it will store the upper hull of the points we have processed so far. So we need to get this process going. So we need to get this started somehow. And so we'll start by putting the first 2 points in the stack. So now we have a stack that contains P1 and P2. Push P1 and we push P2. This is the top of the stack. And we've now processed P1 and P2. Now, is this the upper hull of P1 and P2? That was my whole point set. That would be done. That's that part of the upper hull. Now we want to take the next point and process it. So the next point is P3. So I will, what should I do in this case? Let's see if we can discover the algorithm. Yeah? Just push it onto the stack. Take P3 and just push it onto the stack. And indeed, this is the upper hull of these 3 points, P1, P2, and P3. Now comes P4. What should I do? Yeah. Compare P3, P4 with P2 and P4. Do what? So somehow P2, P3, and P4 matter. Yeah? Yeah. Let's take a look at what happens when we walk from P2 to P3 and then off to P4. So if we walk from P2 to P3 to P4, we make a left turn. Is that something that's going to happen on the upper hull? No. When we walk along the upper hull, we're always making right turns. So for example, here when we did P1, P2, P3, actually if we had done the same test, P1 to P2 to P3, that's a right turn. But here we would make a left turn. So what does that mean? Something's got to go. Yeah. So that means P3's got to go. Because if we put it on the hull, we're going to have to make a left turn as we go from P2 to P. As we travel from P2 to P4 on the hull, we would make a left turn at P3. So that's not something that happens. We do the same test from P1 to P2. So the top two items on the stack, I check to see what kind of turn I make as I go along those two things to P4, and this time it's a right turn. So that's good. I can keep P2. Everything else before that will still be right turns leading up to that if there were more things. So I just put P4 on the stack. So what did I do? The general procedure is something like this. When I want to do PI, so I write something like while stack size bigger than 1, and top to stack items and PI, make a left turn, then I will pop something on the stack. And then once I've done that, this new element that I'm just adding, I know for sure it will actually be on the upper hull so far, because it's the thing with the largest export in it so far. So it's definitely going to be on the upper hull. So after this while loop is over, we do a push PI, and then this whole thing is wrapped in a for loop where I equals 1. And this is what we do. Right, 3 to n. Push P1. Start with the first two items on the stack, then we process the next item, starting on the third one, and using this one. Okay. All right, so let's just make sure we know how this works. Next item is P5. What happens there? Yep. We push it because P2, P4, that's the top two items on the stack, and P5, they make a right turn. So P5 just goes right on the stack. And then we get to P6, what happens? Yep. We're making a left turn. Top two items on the stack, P4 and P5. They make a left turn up to P6. So that means P5's got to go. Then what? Yeah, top two items on the stack, P2 and P4. Going to P6, they make a left turn, so P4's got to go. Now these two items are on the stack. P1 to P2 to P6, that's a right turn. So now we just add P6 to the stack. So as we're doing this, we're getting this, we've actually, in the history of this thing, we're actually somehow getting a little tree on these points, and the topmost path in the tree is going to be the one that ultimately gives it. And now finally, P7 comes in, and we check, P6, we check P2, P6, P2, P6, P7, that's a right turn, so we just push it right ahead. So the algorithm terminates with P1, P2, P6, and P7 on the stack, and the claim is that's the upper hull of this place. Okay. Is that clear? Yeah.
This seems like it's already linear time because you only have to compare, make any comparisons to find the right path.
Yeah. should be linear time. There's a little bit of subtlety here, maybe, because if you look at this thing, just really briefly, what you see is two loops, two nested loops. One of them has n minus 3 iterations in it, or n minus 2 iterations rather, and the other one we don't know. It's a while loop inside here. So at a very quick glance on the surface, you might say this should be n squared. Because this for loop executes n minus 3 times, n minus 2 times. And this while loop, this could execute in one iteration of the outer loop, this could execute n times, right? You can build up a big upper ball that looks like this, and then the next point is way up here, in which case you've got this big stack full of stuff, and then this guy comes along and you have to pop everything off this stack. So we have to argue a little bit more carefully just to say, well, why can this not be something like n squared times? And why is that? Yep. Yes. So at each step through the for loop, we push one element on the stack, and at each we push two elements to start with. And we're careful here, and this condition here says as long as the stack size is bigger than 1. So we never pop off a stack that's empty, which means we never do more pops than we do pushes, and we only did a total of n pushes, so we can only do a total of n pops. So this line of code here does not execute more than, it'll be in fact n minus 2 times in total. Sometimes it might execute 5 times in one iteration, it might execute no times in the next iteration, it might execute n over 2 times in some iteration, but in total, it will only execute n minus 2 times. N minus 2 because we know by the time the algorithm finishes, there's at least 2 points on the upper hall, and so we didn't pop those 2 off. Okay. So step 1 is to sort in n log n time, and then step 2 is the actual scan, and that's just O of n time. Nice, clean loop like this. The only sort of detail hiding from this code is how you implement this right or left turn test, and I explained to you that that's just taking the determinant of some matrix. You have to be a little bit careful about that. If you use floating points, if your input is floating point numbers, then you can make small errors when computing the determinant. In particular, if things, 3 points are almost collinear, then it may be difficult to tell whether it's a left turn or a right turn. The nice thing about that is if the precision of your data is so close to being a left or a right turn, then sort of both answers are correct. Close enough for guessing the shape of the point set. Okay. Good. So, any questions about gram scan? Yep.
Just to do the bottom side, you just check if it's right.
To do the bottom side, you could just invert the right turn, left turn part of it, or if you like, you can scan the points in disorder, in which case then you're also just doing right turns. So scan them in right to left order. This is maybe preferable because then if you take the upper hall and the lower hall and concatenate them, you actually get a walk around this thing in counterclockwise order. So that's usually what the output for the convex Hall problem should be a walk that starts at some vertex and goes all the way around consistently. Good. So it was nice to be a computer scientist in the 1970s. You become famous from simple algorithms like this that were undiscovered. All right. Now I want to show you something substantially more difficult, but still discovered back in the 70s. And that is an algorithm for reporting line segment time. I like this algorithm because it's because it's interesting, and I like it for this course because it uses a lot of data structures. So I have a bunch of line segments here, n line segments. So a line segment is just specified by its two endpoints. So that's like four numbers associated with each line segment, the two coordinates of each endpoint. And what I would like to do is, know if there's any pair of line segments that intersect, and if there are, then report the, either the coordinates of the intersections, or probably more useful is to report the pairs of segments that actually cause the intersection. So here I would like to say there's an intersection between this segment and this segment, and there's an intersection between this segment and this segment. If you want to know where it is, you can just compute it. Okay. And I'd like to do that efficiently. So this is almost line segment intersection report. So here's a stupid algorithm for this problem. It looks like this. So let's say my segments are S1, S2, up to Sn. Then I can say for I equals 1 to n minus 1, or j equals I plus 1 to n, if Si intersects j, then report the pair Si Sj. You want to know all the pairs of line segments that intersect? Well, I'll look at every pair of line segments. I'll check if they intersect, and if they do, then I'll report them. That seems like a decent algorithm, right? So what's the running time of this algorithm? N squared. So we've got this outer loop that runs n minus 1 times, and then this inner loop will run, the first time it will run something like n minus 1 times, the next time it will run n minus 2 times, the next time it will run n minus 3 times, n minus 4, all the way down to 1. And we've seen that means that this line of code here, this check, executes 1 plus 2 plus 3 plus 4 up to n minus 1 times. And even the 9-year-old can tell you that that's n times quadratic time algorithm. Can we do better than that? do better than that? Or is this the best possible algorithm? This is a trick question. The answer is no, it's not possible to do better. And the answer is also yes, it's possible to do better. But let's see why it's not possible to do better. Here's a set of line segments. N of them. And they have the property that every segment intersects every other segment. So how many pairs of intersections are there? There's n choose 2 pairs of intersections. So n choose 2 pairs of intersecting segments. N choose 2, well, remember that's n times n minus 1 over 2. So somehow this thing here, if it runs on that, then it needs to execute every one of these tests because they're all true, and it has to output each of these things. So for this input, it can't do better than that. I mean, it has to report all those things, and so it will have to do that. So in some sense, this algorithm is optimal. And the way we would talk about this normally is we would say that this is what's called worst case optimal. And the reason is that the size of the output can be quadratic in the worst case. Or more precisely, there exist inputs where the size of the output is quadratic. And so we can't, for those inputs, we can't do better than outputting all of the pairs of points, all of the pairs of segments. That's fine, but not completely satisfactory because maybe the input that we're actually given, or maybe most of the time the inputs that we're given will be more like this, where there's only a couple of intersections. Or maybe actually we just want to use this thing to know whether the intersection is 0 or bigger than 0. Whether the intersection is 0 or bigger than 0. And this algorithm doesn't really help in that case because it's still going to check every pair. So what we would like is something that's called output sensitive, where we can write the running time in terms of the number of line segments that we're given, plus the amount of stuff that we have to output. So we have 2 parameters now. N is the number of line segments, and K will be the number of intersecting pairs of line segments. And this is an input parameter. It's just the number of line segments we're given as input. But this thing here, this is actually something we have to compute. We don't know this in advance. So this is output. In fact, it's the size of the output. We have to output that many pairs. And what we'll find is an algorithm whose running time is O of n plus k log n. So k is small. If k is only a couple of 2 or something, then this will just be n log n. In fact, even if k is pretty big, even if k is close to n, then this will still be n log n, right? Because n plus k will then be 2n. This is 2n log n, and that's O n log n. Yep.
So there's no way that
not that easy to know how many intersections you will have before looking for them, before testing them. So there are some things you can do, but they're a little bit more advanced than we're going to cover today. So we'll give an algorithm that has this kind of running time. And so k is small, great, it's an n log n time algorithm. And if k is big, well then this becomes, k becomes the dominant term. So for example, if all of them intersect, then it becomes k log n, or in this case n squared. Which isn't too bad because we know that we can't do better than k. And it turns out for other reasons you can't do better than n log n. We won't prove that today. Okay. So let's see how this works. So this is an algorithm invented by one really famous computer scientist named John Bentley, and the other one was famous-ish, but not as famous, Ottman, not as famous, we've got to know his first name, for example. It's called the Bentley-Ottman plane sweep algorithm. So what we're going to imagine is that we start with this vertical line that we start off over here at minus infinity. And we're going to play a little movie where we imagine sweeping this line across this thing. And all the time, we'll keep track of the intersections of the line with the segments intersect. And then sometimes, we'll reach a situation like this, where we're keeping track of all these intersections, and then we see that two of those intersections become one, at which point we come across. Okay. So we're going to use a few data structures for this. Two, precisely. One of them is going to be a binary search tree, or a skip list, or some kind of sorted set. So we'll have a thing called the screen. The sweep line status structure. This is just a sorted set that contains what's called a sweep line L, the intersections of L with the segments. And it's going to contain those as we move this line along. So those will change. Sometimes we'll do things like a new segment will appear. Sometimes segments will cross. Sometimes segments will disappear. So we have a sorted set that represents this thing, and the ordering is ordered by Y coordinates, so top to bottom, the way the intersections occur in order along this line. We'll also have something called an event queue. This is a priority queue, probably some kind of key, that stores X coordinates where interesting things happen. And interesting things are, well, the start of the line segment, the end of the line segment, queue called the event queue. It's going to keep things ordered by X coordinate, and it's going to keep all the interesting events. And some of these events we know about before we start. So the first thing we do is we take all the endpoints of the segments, their X coordinates, and put them in the event queue. So down here, here's my event queue. I will have an event here, an event here, event here, 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 here. Okay. So if I have n segments, then the first thing I do is I put in 2n events into the priority queue. The starts, the left endpoints of the segments, and the right endpoints of the segments. Okay, and now I start with my sweep line off at minus infinity here. So off at minus infinity, is there any segment that intersects my sweep line? So this thing gets initialized as just an empty sorted set. So it takes a long time to get from minus infinity over to here, to where things get interesting. So when's the first interesting thing happen? Yep. Yeah, so the first interesting thing happens when this line intersects, the first time this line intersects a segment. So how would we get that? Yeah. So we just pull the smallest value out of this priority queue, which is what priority queues do, right? They can extract the smallest value. And that tells us, fast forward past the part, the infinitely long part where you're zooming in from infinity here, and that's boring. The first interesting thing that happens right here when the line touches the first segment. Okay. When that happens, we add this segment to our sorted set. So it appears now in this, on the sweep line, it appears in this sorted set. Okay, when is the next interesting thing that happens? So this is gone from our event queue. Yep. What's that? So the start of the next line segment, which is again the next thing in our event queue. Here it is. So now, the sorted set, which is being used to represent this line, contains two things. It contains this one, and it contains two segments. This one and this one. Now wait a minute. We're putting segments into a sorted set based on some relationship that they have. Can you always compare two segments? Can you always say it one? Yeah, well, I mean, can I compare these two segments? Which one is above and which one is below? So in general, if I say, here's two segments, which one is above and which one is below, then who knows? That should mean different things depending on how you interpret it. But if I say, at a particular x-coordinate, this particular x-coordinate, which one is above and which one is below, that has a very clear answer. This one is above, this one is below. The only time it doesn't have an answer is maybe when the segment, the x-coordinate doesn't intersect one of the segments, in which case, who cares? It's not going to be part of our status. Or when this vertical line goes through the intersection, so that's exactly the kind of thing we're looking for. Yeah.
So when we add the next so you can check if the queue will have both of them, whichever is the higher goes to the first section.
Yeah. Okay. So let's take a look at what happens next. So we put this new thing into this thing. It has these two elements in it. And we also do some checking. And we'll see what that checking looks like in a second. So the next event, but for now nothing interesting happens. The next event happens here. So we fast forward this movie until the street line is here. And now we have three things, this, and this, stored in the event queue. And we'll fast forward again. Now we have this, and this in the event queue, and we're adding this one. Now, here's the trick in general. When I'm adding a new segment to the event queue, so that is a picture, this is colors. This is, not the event queue, the streetline status. So the picture looks something like this. There's some things that are already intersecting. We've already swept over this part, already intersecting. And then there's a new guy that we're adding. We just reached his left endpoint. So, we search for this in the structure. We find this, here it is. This is where it goes in the sorted set in between these two elements. So this is where when we insert it, it's going to go. And now we do a little check. We check to see, does it intersect this one? And does it intersect this one? So, for example, maybe this one actually does intersect this one. In which case, we don't report this intersection yet. Instead, we just add a new event down in the event queue that says, when we get to this intersection, we're going to, something special is going to have to happen. So pause the street line here at this point. Yeah.
Sorry, are you just calculating the slope to see if
No, these are line segments, so we can do the four orientation counts to tell if they intersect. And then, the point of intersection is, once you know they intersect, you can pretend that they're lines, and now it's just finding the x-coordinate of two lines, where two lines intersect. So you can get that. Okay, so at this point, we have this thing, and this thing in our street line status. We're adding this thing. So we check if this thing intersects this one. It does not. Does it intersect this one? Yes, it does. So we add a new event to our event queue down here. Intersection event. It's a different kind of event. It's not a left-hand point or a right-hand point event. It's an intersection event. And now we jump to the next event in our event queue. And the next event in our event queue is actually this one. So something is leaving our queue. So this thing is leaving the queue. So we're leaving the sweep line status. So we take it out, and now we only have three things. 1, 2, 3. Those things are intersecting. If we look at the general picture, so that's a picture that looks like this. Somebody is ending. There are other things continuing. Is there anything we should check for when we take this out? So when we insert something into this sweep line status, we check, the thing just above it and the thing just below it. Is there an intersection there? And that finds some of the intersections. But it doesn't find all of them. When we remove something, do we need to check something? Do we need to do a check? Well, we can look at this thing. For example, these two could intersect. This line and this line intersect. But back when we inserted those two lines, they weren't directly beside each other on this thing. There was this other line in the way. So when I inserted this guy, I would check, does it intersect this? No, it doesn't. Does it intersect this? I don't know, maybe it doesn't, maybe it doesn't. And the same thing when I inserted this guy, I would check it against this one and this one to see if they intersect. But I never checked these two lines to see if they intersect. But when I remove this, these two lines are now adjacent. They're right beside each other in this sorted order, and they could potentially intersect. So when you remove something, when you remove an endpoint, there's a line just above it and a line just below it, and you check to see if those two things have intersected. If they do, then you put that in the event queue. And in this case, we would remove this, and we're checking if this intersects this, and they don't. That one does not intersect that. So we don't put anything in the queue. And now we advance to the next event. Here is the next event. It's this intersection event. And good, so that's the intersection event. We can finally get to it and say, here's the intersection, we report it. Anything else we should do? Yep. Yeah. So before this line, we had, A, B, and C in that order intersected by this thing. But as soon as we skip over the intersection, it's going to be B, A, and C, which means in this example, A and C were never beside each other, but now A and C are right beside each other. So we should check to see if they intersect. This could be the first time they've ever been beside each other, but we've never checked them yet to see if they intersect. And indeed, in this case, they do intersect. So we find that intersection and we add it to the event queue. And the more the general picture, so this is what happens when we reach a left endpoint. This is what happens when we reach a right endpoint, so the end of the line segment. This is the start of the line segment. And when we reach a crossing, we have two segments that cross, and above that crossing point is some segment, and below that crossing point is some segment. We check this one to see if it intersects this one, and we check that one to see if it intersects that one. Put those things in the event queue. And the whole thing is going to work because if two segments intersect, then there'll eventually come a point where the sweep line gets so close to this intersection that those two things have to be side by side. There's nothing else sneaking in there and blocking it. The one little lie that I'm telling you here is if you have a whole bunch that intersect at a common point, then it becomes a kind of mess that you can still deal with. But let's just pretend that that never happens. But so in general, if two things intersect, then eventually they'll, just as you get really close to the intersection, by the time you get there, they will have come beside each other in the sweep line, and the first time that happened, you will have added their intersection event to the event. So then we can finish this thing up. The next event is this intersection event. So the sweep line advances to there. We report that intersection event. We check to see if this intersects something below. There's actually nothing below. We check to see if this intersects what's above. There's something above, but it doesn't intersect. And then the rest of this is just all events of ending this. Here we end the segment. We check to see if these two intersect. They don't. Here we end another segment. Well, now we only have one segment left in the structure, so there's nothing to check. Here we end a segment. There's nothing left in here at all. Here we start a segment. There's nothing to check. This is the only segment in the structure. At this point, we start a segment. We check to see if this one intersects the one beside it. doesn't, and the segment, and the segment. No, we're not. So it's just it's like a movie that we're playing that keeps track of all of these intersections of these lines with the sweep line. And it's just, you can't play this movie continuously because we don't have an infinite amount of time to wait to do so many things continuously. So we find these discrete events where we can fast forward the movie to where the interesting stuff happens. So this is really, this is an algorithm for computing a specific problem, or for solving a specific problem, but really the way it's doing it is by running a simulation of a continuous process and getting it that way. Okay, so if we look at the running time, let's see the kinds of things that we do here. So basically, the first step is to so the first thing we did was we added 2n endpoints to a priority queue. So how long does it take to add something to a priority queue? So to a heap or a randomized nullable heap. It takes log n time. So if we do 2n of these things, that's going to be O of n log n. All right. Eventually, we're going to remove each of those things from the priority queue. So we will end up doing 2n removal endpoints from the priority queue. And removing something from a priority queue takes O log n time. So removing all of those endpoints, and they do all get eventually removed. At the end, there's nothing left anymore. So removing all of those, that part of the algorithm is going to take n log n time. We also add things to a sorted set. So we sometimes take a sorted set and we add an item. How many times do we do that? Yeah. No. N times. So each time we come across additions in a sorted set, those are left endpoints. That's log n each for a total of n log n. We also do, when we sweep the right endpoints, we do n removals from the sorted set. So that's all of n log n. So what are the other operations that we do? We check for intersections. And when we find an intersection, what happens? So every time we find an intersection, and if this algorithm is correct, we find them all, we add it to the priority. So that means we do, additionally, k insertions into a priority queue. That's going to give us k log n. Well, eventually we're going to remove all of those, but it's not just insertions, but also removals. That's still only k log n. Anything else that we do? at these crossing events, something a little bit funny happens. We have a dictionary which is storing these segments, or sorted set which is storing these segments, and it's storing them, 1, 2, 3, 4 in that order. And we're now about to step to the other side of this crossing, and so now this sorted set needs to store those 1, 3, 2, 4. So we need to swap two elements in that sorted set. Depends what your sorted set looks like. Sometimes that's easy to do just locally. Like you could, in a skip list, you could actually just do this by changing a few pointers. But perhaps the easier thing to do is to just remove one of them, change the x coordinate, and then reinsert it so that it gets inserted back in the right place. So that's another k removals and additions in that sorted set. K removes and adds in the sorted set. So that's another k log n. So what have we got? K log n, k log n, n log n, n log n, n log n, n log n, which is n log n plus k log n, just like the formula says. So we can report all the pairwise intersections in a set of these line segments in order n plus k log n times. What if I just wanted to know if they intersect or not? Could I do it faster? What if I just had a bunch of line segments and I just wanted you to tell me, is there any intersection or are they all completely disjoint? So if they're all disjoint, what happens when we run this algorithm? It runs in n plus k log n time, but k is 0, so it runs in n log n time. So that's good. If they're all disjoint, it runs in n log n time. And well, if there's an intersection, then we run this algorithm, and at some point, two things become adjacent that intersect, and then we can stop and say there's an intersection. And that'll happen before n log n time, because if we stop the first time we've detected one of these intersections, then we haven't done anything, we haven't done any of these k insertions or k deletions or k removals yet, so we're still only done these n log n operations. So if all I want to know is if two things intersect, then I can get that in n log n time. And of course, that's a tremendously useful operation because don't think of these things necessarily as just disorganized line segments, but these line segments could be objects like this. No intersection so far if you don't count the endpoints as intersections, but then you've got another object like this. I'm trying to figure out, do these things intersect at all? The inside of that. And indeed, these do intersect, and you can use this to detect this kind of thing. So again, this convex hulls and this line segment intersection testing, both of them can be used. One gives you a rough idea of whether two objects intersect each other. You check their convex hulls very fast. If their convex hulls do intersect, then you can use something like a plane sweep like this to know whether there really was an intersection, or maybe they just fit together perfectly and don't intersect. But you'll find it this way. Okay, so that's a good place to leave it for today.
Joe, you're on TV.
I am pretty popular. See ya. Monkey ball there.
Yeah, it's like
It's the same business course that you did on
I'm gonna walk backwards because I'm fancy like that.
So whatever these segments are, we will just go, use start and end. So we are building the first, start point, and when, okay, this is like, I'm not going to speed. Now I want something which is bigger than what I was doing before, so now this is keep doing it until, like, there's no more segments, yeah.
Huh? Nothing like a quality song. Maybe sub 11:30. Oh, that's what you did do. I just don't want that better though.
I'm surprised that.
The last mailer was yeah.